I'm going to skip over it. Okay. Next question. Rank the following molecules in order from strongest intermolecular forces to weakest. This is chapter 8. Okay, intermolecular forces. So, little review here. We have London dispersion, also known as van der Waals. These are the weakest. We have dipole, dipole interactions. Okay, these are the next strongest. And then we have hydrogen bonding. And these are the strongest types of intermolecular forces. So I'm going to just take A here. We have a molecule of nitrogen. And let's work this out. First, draw out the Lewis structure. We need to determine if these are polar or non-polar molecules. If they are polar molecules, then they will experience dipole-dipole interactions. Unless they meet the criteria for hydrogen bonding, then the strongest force there would be hydrogen bonding intermolecular forces. If it's a non-polar molecule, the strongest type of intermolecular force that it would have would be a London dispersion or a van der Waals force. So let's look at a molecule of nitrogen. The Lewis structure looks like this: a triple bond, a lone pair on each nitrogen, and this is a non-polar molecule. The electrons in this triple bond, they're shared evenly because the nuclei or the nucleus in each nitrogen atom is identical, so they're both pulling on those shared electrons with the same strength. So this is a non-polar molecule. So we have, I'll abbreviate, London dispersion forces here. Okay, B, we have hydrogen, carbon, and nitrogen. Well, we know hydrogen can only have one bond. The nitrogen needs 3 bonds, and the carbon will need 3 more bonds. So I'm going to triple bond those things, and I know nitrogen gets a lone pair. So there's our Lewis structure. When we look at this molecule, we know that carbon-hydrogen bonds are never polar. But a carbon-nitrogen bond, if we were to look at, an electronegativity chart, I should have had one handy. I can pull one up really quick. Electronegativity chart. I will provide one of these on exam 3 for you. I'm trying to find, it'll be in this lecture. Electronegativity. That's chapter 4, so I'm going back to our molecular compounds lecture to find the electronegativity chart. We see that a carbon-nitrogen bond, the electronegativity difference there is 0.5, so this is a polar bond. This triple bond is polar. And if we draw in the partial positive, partial negative, we'll have partial negative on this side, and this side of the molecule will be the partial positive. So we have a dipole here, is what I'm trying to say. This is a polar molecule, so the strongest type of force it will experience is dipole interactions. Okay, molecule C, we have carbon tetrachloride. Should be a fairly straightforward structure to draw. Put all the lone pairs on your chlorines. And there's tons of symmetry here, which means even though the carbon-chlorine bond is a polar bond, you have 4 polar, I don't know what happened, sorry. We have 4 polar bonds. The carbon-chlorine bond is a polar bond, but because there's symmetry, if we draw in all the dipoles, okay, so all these chlorines are partial negative. And this carbon is partial positive. So we draw in all the dipoles pointing, we see the up and the down dipole cancel, and the left and the right dipole also cancel. So because of that, this overall is a non-polar molecule. London dispersion is the strongest type of intermolecular force between carbon tetrachloride molecules. Okay, D, ammonia, NH3. Here is a molecule of NH3. Nitrogen has an electronegativity value of 3. I'm looking at my electronegativity chart. Hydrogen 2.1, so the difference there is 0.9. So this is certainly, these nitrogen-hydrogen single bonds are certainly polar bonds, which means all of these hydrogens are positively polarized. We also have a nitrogen with a lone pair, so we meet all the criteria for hydrogen bonding here. So hydrogen bonding will be the strongest kind of an intermolecular force for a molecule of ammonia. Okay, E, CH3Cl. So that molecule has a carbon with 3 hydrogens attached, and then the 4th bond is to a chlorine. We just figured out on molecule C, carbon tetrachloride, that the carbon-chlorine bond is polar. Okay, so in this bond right here, carbon is partial positive, chlorine is partial negative, so we do have a dipole here. There's no symmetry in this molecule, so that makes it a permanent dipole, and the strongest type of intermolecular force then is a dipole-dipole interaction. Lastly, we have CH3COOH. So CH3, that should be fairly straightforward to draw. Carbon, 3 hydrogens. Then we have another carbon, and it's got an oxygen attached, but we know that oxygen has to have 2 bonds, 2 lone pairs, so I'm going to double bond it to the carbon. And then we have another oxygen with a hydrogen. Now, pause. Why could I not have just drawn it like this? If I would have done that, if you notice, this carbon is left, I have to erase one of these bonds. This carbon is left with only 2 bonds, so I cannot draw the molecule like this. I have to take this OH group and I have to attach it to the carbon. So let me erase so that I can neatly do that. Carbon always has to have 4 bonds. Right now it has 3. If I put the remaining OH group right there on that carbon, 2 lone pairs on this oxygen, now everything is satisfied. Each oxygen has 2 bonds, 2 lone pairs. Each carbon has 4 bonds. All the hydrogens 1 bond. This is just basic rules of Lewis structures from back in chapter 4. So if this is confusing to you, make sure you go review rules for Lewis structures, because that does play into chapter 8 material. Okay, now we need to ask the question, is this molecule polar or nonpolar, and does it have the requirements for hydrogen bonding? Well, we definitely have oxygens with lone pairs. That's one requirement for hydrogen bonding. And do we have any positively polarized hydrogens? Well, remember the carbon-hydrogen bond. Are any of these positively polarized? No, because the carbon-hydrogen bond is never polar. It's only electronegativity difference of 0.4, which is not polar, so none of these hydrogens are positively polarized that are connected to the carbon. But we have one more hydrogen we need to take into account. The electronegativity difference between hydrogen and oxygen, if you look at an electronegativity chart, it has a value of 3.5, and hydrogen has a value of 2.1. So the difference there is 1.4, which is definitely polar. Okay, so this hydrogen, what we're ultimately trying to decipher is, yes, it is positively polarized. And like I said, we have lone pairs on oxygens here, so we meet all the requirements for hydrogen bonding. So the strongest force here will be a hydrogen bonding. Now, we've done a ton of work, all to answer this question, which says rank the following molecules in order from strongest to weakest. Okay, so if we have 2 molecules that will hydrogen bond, we don't know which one actually is the strongest. So we have D and F, they both hydrogen bond. So I'm not going to be particular about what order we put D and F in, which one goes first. They both hydrogen bond. So I'll just write D and F. Okay? Those will go first. We're going from strongest, which is the hydrogen bonding forces, to weakest, which is the London dispersion forces. So after we've listed all the molecules that can hydrogen bond, next strongest would be dipole. We have two molecules that will have dipole intermolecular forces, E and B. It doesn't matter what order we write them in, because we can't differentiate which one is actually the strongest. So B and E would be next. You could write E then B, it doesn't matter. Lastly, we have two molecules, London dispersion right here, A and C. So I'm just going to write A and C. Okay? So these molecules can hydrogen bond. These are the molecules with dipole. And the weakest, these are the molecules with London dispersion forces. Okay, so that's an appropriate order or ranking for this problem. Okay. Next up, we have the reaction of carbon monoxide with oxygen. How many problems do we have left, by the way? 1, 2, 3, 4, 5. We have quite a few. I'm going to do this problem and then we'll pause this video and pick up with another one. The reaction of carbon monoxide and oxygen produces carbon dioxide. Write the balanced chemical equation. So we have carbon monoxide, CO, this is a gas, plus oxygen, O2, this is a gas, and that makes carbon dioxide, also a gas. We said a balanced chemical reaction, so we have 1 carbon and 3 oxygens on the reactant side, 1 carbon, 2 oxygens. So if we put a 2 here and a 2 there, now we have 2 carbons on both sides and 4 oxygens on both sides, so we're balanced. Then it tells us the equilibrium concentrations at a certain temperature are, and then it lists all these molarities for all of our reactants and products. And then it says write the equilibrium expression and solve for K. So here we will plug in numbers and we will get a value for K. And then we're going to make a comment about at equilibrium are reactants or products favored. So let's write the expression for K. Remember, it's concentration of products raised to the power of their coefficient over concentration of reactants. Everything here is a gas, so we don't exclude anything. Remember, you exclude things that are solids or liquids, so we'll write CO2 squared divided by the concentration of CO, carbon dioxide squared, times the concentration of oxygen. Coefficient is 1, so it's raised to the power of 1. Okay, now we plug in the numbers. So CO2, its equilibrium value was 0.11 molar. We're going to square that. On the bottom, CO is over here, 0.025 molar, and we're going to square it. Concentration for oxygen is 0.015 molar. We just raise it to the power of 1, so you don't have to write anything. Now you just do the math. So we'll do, I'm going to do the denominator first so I can do it all in one go because I have a fancy cell phone calculator. 0.025 times 0.025. So that is 0.000625. And then times 0.015. Okay, so I'm going to continue my math up here. K equals 0.11 molar squared. And on the bottom, I have, how many? That's a lot of zeros. 1, 2, 3, 4, 5, 6. I have 9.38 times 10 to the minus 6. Okay, So we'll do 0.11 times 0.11 because that's 0.11 squared. And when we do that, it makes this numerator 0.0121. Now I'll divide that by 0.1234593 Okay, just double checking my math here. So I get that K equals 1,290, 1,289 point, we'll just say 98. There's no units here. K is a unitless value. We see that K is much, much bigger than 1, which means that products are favored. Okay, products. And that is the end of this problem. So I'm going to pause